Hello, welcome. Welcome at this live event where we are going to talk about managing tool deterioration. Could be perhaps the most important thing there is in machining. It's for sure the most complex thing there is. Tool deterioration and how to manage it. My name is Patrick de Vos. I'm your host of today, and together with my young colleagues behind the scenes then, and they look a little bit stressed, but I think we'll manage. Welcome at this session where we are going to talk about tool deterioration. Tool deterioration and tool deterioration is under the umbrella of troubleshooting in machining. And when we use the word troubleshooting, machining people, they act a bit fishy, I always have a feeling. It's like we talk about a car, we need a car, and we discuss a car and so on, and then at one moment we reach consensus, we say, okay, this is what we think we need. And then machining people, they always say, yeah, but wait a second, before we take a decision, let's discuss troubleshooting. And I find that so strange that the decision of what to use is governed by the we suppose we are going to have lots of problems. It's just something I want to share before we go into this. But it's I find it strange. Now the basis, we always go to the basis when we talk about machining. It's about the machinability model we use, and machining is a process where material is removed from a workpiece under the form of we share the material off, we deform it, and we share it off. And this process, this physical process, there are variables influencing this process, variables that are coming from the loads which are acting on a cutting tool, and there are other variables that gives us an idea about the load bearing capacity of a cutting tool. And we work with those variables, we combine them, and we take into consideration all the different phenomena that we see appearing during a machining process. You have the mechanical things and the thermal things, and having control over a machining process means that having insight in these variables and having also insight in the relation between these variables, how they relate to each other to end up in a final result, which is hopefully a well-controlled machining process. And in the end, asking the question, did I make the correct decisions? Did I solve this equation in a correct way? It's in machining, that's pragmatic. In machining, we say, okay, look at the result, look at the tools after a while, how they look at the workpieces, how they look, talk to the people that are there during the process, the operators that can explain what they observe during the process. And based on that, we decide, okay, this equation was solved correctly and it led to the wanted result, or no, we need to make modifications. Now, today we are going to concentrate on wear, deterioration of cutting edges, which is a very critical thing in a sense that it tells us how the machining process took place. And we can learn a lot from that if we know what to look for. Now, let me start by talking a little bit about deterioration, tool deterioration. What exactly is it? And in 30 minutes, of course, we cannot answer all the questions here. And what I would advise everybody is to consult the literature, or perhaps participate in one of the master classes we organize on this subject. Here today, in 30 minutes, I can ask the critical questions. I can ask the questions which needs to be asked, and I explain later on why these questions needs to be asked. First, what is tool deterioration? What is deterioration? Deterioration is a physical thing, and it means that something loses the ability to perform in line with expectations. You can even bring it to humans. We also have physical capabilities, and those deteriorate. As we are getting older, our physical condition deteriorates. And it's a fact of life. That's a very important thing to consider here, because deterioration is normal. It's part of life. It's how it goes here on this world. Of course, we have to be a little bit more critical than just saying it's how it is, because there are different types of deterioration. There are different deterioration things happening due to aging. People get old. Tools are being used and they wear out. That's aging deterioration. You also have sudden impact deterioration. That are the things that happen suddenly. You can break a leg. And that keeps you away from performing up to normal expectations because you broke your leg. You can break a cutting tool, and that also will end the lifetime of the cutting tool. But this has nothing to do with age. This has nothing to do with time. This is a sudden impact event that leads to a situation where we cannot perform anymore. So here we have to be a little bit more critical, although I say we have to live with it. It's normal, yeah, but not each type of deterioration we should accept. We should be critical there. And you also will see that deterioration phenomena, wear phenomena if you want, there are different types. And a very important thing when you are working with this, when you try to manage tool deterioration, is that you have to ask yourself the question, which one is predominant? Which one is the most important? Which one really will lead after a while to a decision of, now it has been enough, now I change the tool? And that's a very important thing to keep your eyes on, that we take that decision, which one is preferred. Because I say, okay, deterioration is part of life, we live with it, but we will see different types of deterioration taking place. But for sure, you have a preference. You in a certain situation, you can say, okay, I would like to see this. I accept the reality of it's happening, but under which form do I prefer it to happen? And what's the frequency? Now, a broken tool is not nice. And people, sometimes they panic. They say, oh, I broke a tool, big panic, stress. Yeah, but does this happen just once, that tool breaks? Or does it happen structural each time again? And that's two basic different situations. When it happens once by accident, don't make life difficult. If it's an accident, yeah, replace the tool and continue. If I go back to my comparison with a car, of course, sooner or later you will have a flat tire. There's no reason to panic. Just replace the tire and drive on. If, of course, every second kilometer you have a flat tire, you have another problem. So what's the frequency of the things you see? And what are the consequences? Because we always talk like deterioration, and this is important, and we have to keep our eyes on, and we want to manage it. But think one step further. If I see a certain type of deterioration, and I have all my discussions about, is this predominant, is this preferred, is this desire, what are the consequences of certain types of deterioration? These are basic questions. And the physics behind this, in a nutshell, as we have very limited time here, take the comparison of high pressure cleaning. Now, calm. Perhaps you think now high pressure cleaning, what is this about? But I just use this as an example to let you understand what deterioration, physically, what is it? You have a surface with a layer on. You have a floor with dirt on. You have a cutting tool with cutting material and a coating on. and you have workpiece material, in this example represented by the liquid which is used for the high pressure cleaning. That's your workpiece material. And you have geometrical factors. How you hold this thing is going to influence the result of this. And you have cutting conditions, you have pressure and the temperature of the liquid and the composition and all that type of stuff. And this leads to a situation where the two meet, the floor with the dirt and the high pressure liquid you use to clean, there things starts to happen. You have mechanical loads acting and thermal things are happening and chemical reactions take place and situational loads. And the result is that after the operation, your surface looks different. The surface is modified in structure, in shape, dimensions, composition, properties. You have a different surface. Now back to my machining, it's exactly the same thing, you know. You have your cutting tool with a coating on and a material and a geometry, and you have the workpiece material, and the two are in contact, and where they are in contact, you have all these loads acting back and forth, action and reaction. And that leads to a number of things, but the thing we are interested in today is it leads to a modified surface on the cutting tool. We refer to that as deterioration, tool wear, if you want, if I concentrate only on the aging wear principles. That's it. Very short. I simplify a lot here, but basically that is what we are talking about. And that means that if we see this, it helps us to answer the question on why do we have deterioration? Why do we have wear? What are the physical things underlying this? Well, wear on a cutting tool, deterioration of cutting edges can be due to abrasive working. Abrasion as a physical phenomenon will lead to changed surfaces. It could be adhesion. Abrasion is the first one. Abrasion is, I sometimes say, if people say, what is exactly abrasion? It's a scratching effect. It's like with your fingernails, scratching on your hand. You scratch material away. That's abrasive wear. Adhesion is that materials connect and the connection breaks after a while. And that breaking of a connection leads again to a changed surface of a cutting tool. Adhesion, and more in particular, abrasive breakage, is another physical phenomenon leading to wear on cutting edges. Fatigue, when you have a surface and you submit it to a pressure, intermittent pressure, intermittent mechanical loads, you'll crack the surface and break little pieces out of it. That is fatigue wear, we refer to it. And you also have chemical wear. You have different materials. You bring them together under certain circumstances of pressure and temperature and things. And there are chemical things taking place there. And those chemical reactions, again, will modify the surfaces. Chemical wear. And basically, when we talk about machining, when we talk about cutting tools, these are the four basic physical, chemical phenomena leading to wear. And for me, always, if you see wear on cutting edges, for me, it's automatically. And I would like to invite you also to try to reach that stage that you make that automatic question of what was the phenomenon leading to this wear? Because if you know the why, and if you combine that with variables influencing those phenomena, and there are quite a lot of variables, but the main ones are the application, Do we talk about intermittent machining? Do we talk about continuous machining, turning, milling, that type of thing? Different types of applications lead to different types of wear and wear patterns. The workpiece material, because think on the chemical things, when different workpiece materials are being machined, it could lead to different phenomena. The tooling concept. What is your overall tooling concept? Do you have strong tools? Do you have weaker tools? All of that is going to influence how wear develops on cutting edges. Cutting conditions, the conditions under which there is contact between the tool and the workpiece material. The cutting material, the opposite of the workpiece material, also an important factor. And the cutting geometry. Don't underestimate the cutting geometry. People, when we talk about tool wear, they always concentrate on cutting materials, and very seldomly they talk about cutting geometries. If you have a sharp cutting edge is fragile and breaks easily. The geometry is an important factor. And this gives you an overview of if you want to manage your tool deterioration, this is information that you need. If parts here are missing, it becomes difficult. And even if you have all this information, you still have the butterfly. What do I mean with butterfly? The butterfly effect. You will see that if you are in a situation and you think, okay, I control everything, I manage everything, I know what's going to happen, then something will happen that surprises you. I'm more than 40 years in this, and so often still it happens that I think, oop, I didn't expect this. And you know, in the physical world, everything has a reason, everything has a cause. And perhaps we forgot about it, perhaps we overlooked it, perhaps we misjudged it, but it's a very important thing in tool wear or tool deterioration management. It's the chaos effect. It's the butterfly effect that we have to be aware of. Now, traditionally, when we talk about tool wear or tool deterioration, very traditional people always use what I refer to as the remedy approach. What do I mean with a remedy approach? People look at a cutting edge, they see something, and they start to write a recipe on how to solve this thing. And that remedy approach, basically we say, okay, if we look at wear, some of the wear we can live with. We prefer it because it's safe, it's controllable, it's predictable. We accept it's happening, it's a fact of life, but we manage it. We are on top of it. Other wear patterns are unpreferred because we cannot control them, not manage them really. They happen and they lead to situations which are out of control. A remedy approach is very strongly with this. It says, okay, mainly if I see wear patterns which I do not like because they are not safe, they are not controllable, they are not manageable, I should avoid them. And then the remedy approach starts. If you see this, do this. If you see this, do that. And this you find under the form of written text. You find it under the form of pictures. You find it under the form of tables. Whatever, but it's each time the same thing. You see something, you observe something, and then you receive a number of, instructions. Do this, do this, do this, and then normally you see the wear disappears. Now, I always wonder if people work like that, if they are curing the illness or easing the pain. You know, if you have a headache, and you go to a doctor and you tell the doctor, I have a headache, the doctor can give you a pill so the headache goes away. That's easing the pain. A doctor could also say, yeah, why do you have a headache? And that's curing the illness. And personally, I think that in tool deterioration, tool wear, we concentrate too much on easing the pain. The recipe method, here you have a pill. And we do not spend enough time in curing the illness. And that's why couple of minutes ago when I said there are some crucial questions to ask, crucial questions that have to help us to find out what is the illness. And of course, we have to ease the pain. Basically, we should do both. But the illness, the cause is very important, because, all of this is very nice, but there is that little thing with reality that you think you are fully under control, you manage everything, and then suddenly something happens. And that's reality in machining when we talk about toolware. Because if you look to use tools and if you look at cutting edges, you see that those cutting edges, they show a combination of wear patterns. And yeah, you normally, the remedy approach says, if you see this type of wear, do this, and if you see another type of wear, do something else. But if you look to reality, what you see is a cutting edge on which you see both. And then the question is, what do I do now? And that's why it's so important to ask that questions from a couple of minutes ago. Which one is predominant? Which one in the end will lead to that you have to decide, I stop now? Which one is the one you prefer? Which one is the one you think is controllable? And so on and so forth. And that's the reality. And if you look a little bit, how big or how important is this reality? What you see here is a very typical example. And situation by situation is different, but it gives us an idea. If you look to, if you would take 100 used cutting tools and you start to evaluate what you see on the cutting tools, well, what you see is that roughly 1/3 of them has singular wear patterns. I mean, only one wear pattern you'll find on a cutting edge, not a combination of different patterns, only one, and it's preferred. It's controllable, it's safe, it's manageable, and so on. 1 out of 5 is singular wear, but not preferred. A wear pattern, we say, oh, this is not nice because we cannot really control this. 1 out of 5, you have mixed and unspecified. You see a mixture of wear patterns, but it's not very clear what exactly is it that you see. You will see broken cutting edges. It's a fact of life. Cutting edges break, but it should be accidental. That it should be an accident. If it's becoming structural, the broken cutting edges, then you have a structural problem. And also very interesting, if you see, if you would do an analysis like this, you see that a number of cutting edges, they are thrown in the bin of the used tools, and they were not even in contact with workpiece materials. And that's an interesting thing then, is why do people decide not to use a cutting edge? They spend quite a lot of money purchasing it, and then in the workshop, they just throw it away. Also here, the why question is an important question. Now, I'm talking about a lot of questions here, but the real important question, the one that we really need to be able to answer as good as possible, that is, when do we decide now it has been enough and we replace the cutting edge? I go back to my car thing. You remember in the beginning I said, okay, we talk about the car. Okay, if we talk about cars, when do you change the tires of your car? When is the deterioration so big that you think, okay, this is becoming unsafe, unreliable? And that's a very, very important question. I could give you a very pragmatic answer. You have to change cutting edges 5 seconds before you see this as a result. This is a milling cutter that was used 5 seconds too long. The net result is what you see here. Now, that's very simple, saying 5 seconds, because, very important is how do you recognize you are on the edge of this event taking place. And here we bring in the little sister of toolware called Tool Life. But Tool Life, that's a subject the next time we are going to talk about Tool Life. if you combine tool deterioration, tool wear, and tool life, then we end up in answering this very important question. For today, I just put the question there. I just ask you to think on it. When do you replace cutting edges? When is the moment that you say, now I change? A smart approach to this is you take a couple of steps here. The first step is, if you try to control your tool wear, it's don't concentrate on one cutting edge. Try to have a number of cutting edges that together are representative and meaningful to have a look on. That you can have some structural answers on questions. Do you have all the information? Sometimes people show me a used cutting tool and they ask me, what do you think? Yeah, what do I think? I see a used cutting tool, but is what I see good or not so good? If I don't have the information, the application, the workpiece material, the cutting conditions, I can't say anything sensible. I can just say I see wear. What did you expect? And is what you see in line with what you expected? What did you desire? And is what you see in line with what you desire? Because again, tool wear, tool deterioration is a fact of life. In a big number of cases, it's not a problem. It's happening. In other cases, it's problematic. If what you see in a structural way is not what you expected or is not what you desire to see, then you have a problem. Then we need to take care of that. Which type of deterioration is predominant? As I said, if you break a cutting edge, it's an accident. But if breaking becomes the predominant deterioration factor, then you have a structural thing on your hands. When it's sudden impact phenomena, tool breakage and things like that, as I say, is it structural or is it by accident? When it's aging air, what is the main pattern? Because you will see that they develop together, a number of them. There you have to put your finger on the one which is the important one. And then the question that links to the subject of tool life, in all of this, how long did you use the tools? Because you can see a certain wear pattern and a size of the wear after 5 minutes, or you could see the same thing after 50 minutes. That time thing is important in this context. When we start thinking like this, we developed an instrument. We refer to it as global tool deterioration analysis. Global tool deterioration analysis is based on that smart approach I just presented you. And it's an instrument that helps us to create sustainable and productive machining. Because as I said, managing tool deterioration is perhaps the most important thing there is in machining when you look at the broader picture, that you want to have a sustainable machining process, that you want to have a productive machining process. And the key for this is people. As I say, you remember my butterfly? That despite everything, you'll see things taking place that you think, oh, I didn't expect this. And to take care of that, we need human creativity. Or creativity, I don't know if that is the correct word here, but anyway, we need that human insight based on knowledge. What exactly is going on here? Based on skills, do I know what to do to work with something based on available equipment? Because a workshop, it's not the cleanest place in the world, and often it's not the place with the best lighting in the world, and cutting tools, they are little like this, and you have to look. Equipment is important, and knowing how to use the equipment and the mindset. Do you dare to take a responsibility in a certain decision? Okay, because you will have to take a decision. What is the predominant wear? Is it now flank wear or is it the shipping? Well, which one? So you need to take your responsibility there. And for me, people, when we talk about tool, and I see big potential here for what people refer to as digital machining, but that's another subject. But for the time being, it's people that will be the main factor in all of this, and knowledge. And as I said, in 30 minutes, I can just ask the questions. I invite you to consult specialized literature, participate in master classes we organize on this subject. Knowledge is power here. And I talk here general, but perhaps interesting for you to know, because as I said, one of the informations you need if you talk about toolware is the information of what's the application. But tomorrow there is a webinar, and I would like to, if you are interested in wear in milling application, and even more than that, you are very welcome to come and listen to my colleagues talking about these things, because I treated wear here in a very general way, but as I say, wear is important enough. It deserves that it's put in certain context. What is wear in turning, and what is wear in milling, and what is wear in drilling, and so on. In a very short time, we talked about managing tool deterioration. I started by saying, okay, what do we mean with tool deterioration? Why is it taking place? What do we need to know to be able to control it, to manage it? Be careful. It's a little bit a waving finger I have here. Be careful with the recipe method. Be careful with that you concentrate on easing the pain and that you forget to cure the illness, because then it's going to be a never-ending story. And if you really in a structural way want to work with it, I would say use a smart approach. Don't focus on one cutting edge. Take a sample that is representative, that is meaningful, and ask the important questions. What do I see? What is predominant? How often do I see it? Do I have an idea what is causing it? Because only then I can start working on if it's considered to be a problem, solving it. Most important question, though, is the time. I see a certain wear pattern, a size. Yeah, but after how many minutes in cut or work pieces finished do I see this? But that's the subject of tool life. That's for next time. And there we will combine. I see wear and I see time, and what's a good combination there. I hope this 30 minutes was interesting. Let's see which questions we have on the subject. I have a first question. How power density plays a role in PVD coating? Ooh, this is a question which is interesting, but I have to park this because this question deserves a more better answer than just saying in 5 seconds something. And this is a little bit more into carbide metallurgy than in wear. A second question is an interesting question, because that second question, well, let me, higher cutting conditions help us to reduce machining costs. Since your point of view, what is better, a reliable process or still looking for maximum cut? Yeah, let me ask you a question as a counter question here. If you say, I want reliability, I tell you, use a cutting speed of 0 meters per minute. trust me, you'll never break a cutting tool. You won't produce any workpieces either. If you say, no, productivity is important for me, then you should use 10,000 meters per minute cutting speed. In theory, you are going to have an enormously high productivity, but we all know that that is theory. In reality, yeah, you use up your tools, you wear out your tools so fast that you don't even cut. Constantly, you are changing tools. Somewhere in between, there is the correct balance. And this question from Enrique is asking about that balance. But can I invite you for the next live event on this? Because that is the basic question we are going to try to deal with then. I also have a very long question. Wait, let me quickly read it. Okay, here. That question is about when we talk about wear and when we talk about, because the question that the gentleman here is asking is about the different variables around this thing and how they have impact. He gives the example, for every 1/10,000th tool run out, tool life is reduced by 10%. And indeed, sometimes I say machining is the science of working with correction factors, because indeed there are so many correction factors. If you look to tool wear, you have the principal things. But next to principal things, you have corrections where people say, yeah, if this, that will influence so much your wear, and if something else, that is what I refer to as the correction factors. That's, to be honest, where I see a big future for digital machining, that we can work with those correction factors in a better way. But the rule of thumb that run out is influencing tool life is very correct. If the statement, and I'm concrete answering the question here, if it is absolutely correct to say that 1/10,000 millimeter run out gives a 10% reduction in tool life, I do not dare to confirm, neither say it's not true. It's and this is the thing with correction factors, it's depending on the situation. In general, I think it's rather okay, but really calculating, I don't know. I also have a question here. How is the tab? We still have time, so that's good. It's a question from Adrien, and his question is, would you say looking at the used tool should be the starting point to decide when to change a tool? Or is it a combination of surface finish? You know, 40 years ago, when I started my career in machining, we were having a big project, and it was called adaptive tool monitoring. And the thinking then was, as a tool wears out, and that means the geometry of the tool is changing, perhaps the composition of the surface materials is changing, the structure is changing, basically the process is changing. And if the process is changing, power consumption, vibration behavior, sound emission, noise emission, surface roughness, all of that will change. And the conclusion was 40 years ago that in process monitoring we couldn't work with. For reasons it really didn't work. So we were doing off-process monitoring, and basically tool wear was the signs of we were always too late. As I said, you should change the tool 5 seconds before you break the tool. Yeah, but very often we are too late. I think in-process monitoring is much better, but was impossible in the past. But I think with present possibilities, it's worthwhile to take it up again. So I don't know if that is an answer to the question, but At least it gives you. I share a dream with you now. How beautiful it would be to do in-process monitoring of toolware. Then I also have a question. Time is okay. How much RPM should one maintain to improve tool life of cutting? Now, that's an impossible question. The general rule is, and we will talk next time we are together more about it. The general rule is that the higher the RPM, or I should be concrete now, the higher the cutting speed, the shorter the tool life. And there is a rule of thumb that says if you modify your cutting speed by 10%, you influence your tool life by 50%. So, yeah, the higher your RPM, the higher your cutting speed, the shorter the tool life. The lower the RPM, the longer the tool life. But low RPM means low productivity. High RPM means high product, at least in theory, high productivity. Somewhere in between is the balance. So this question can only be answered if you first tell me how long tool life you want. Only then, this is a question that can be answered. There are more questions? I have here a question. Somebody says prefer tool deterioration. Yeah, but tool deterioration is never preferred. No, I don't agree with that, because tool deterioration is a fact of life. When you use it, whatever we use on this world, it wears out. It loses the ability to perform like it was new. So, and of course, we all want to be old or get old, but how? That is the other question. And you have to see preferred tool deterioration in such a way that we do accept there is tool deterioration, but there are different types of tool deterioration, and some are more preferable than other because some gives us more the ability to manage them, to keep them under control, to predict what's going to happen, to create a process which is sustainable in time. And you have to see like that. So indeed, there are preferred tool deterioration patterns, mostly for those amongst you who are familiar with this, normally flank wear, crater wear, plastic deformation, and to some extent notching, we like to classify as preferred tool deterioration patterns, tool wear patterns, because to some extent we can control them. We can plan, we can work, we can influence them. While other wear patterns think on shipping, think on flaking, things like that. We don't have enough insight today to be able to say we manage them, we control them. Do we have more questions? There is a question here. What is the difference between a micro and a macro geometry? Now, I use the academical terminology here, micro and macro geometry. In daily terminology, the micro geometry is also known under the cutting edge geometry, the edge treatment. You know, cutting edges, they can be sharp, but there can be a chamfer on top of it, or they can be rounded a couple of microns. That thing is what we refer to as the micro geometry. It's the cutting edge geometry. While the macro geometry, with that we refer to as basically the positioning of the rake face and the clearance face, the cutting geometry, we call it in daily terminology. And yeah, we have time for one question more, I think. In the overview of phenomena leading to wear, you do not mention friction. Why? That's a good one. Friction. Now it becomes a little bit philosophical, perhaps, because friction is not a wear pattern. Friction basically is the physical phenomena where the relative movement of two things which are in contact with each other is hindered. That is friction. Friction will lead to certain wear patterns. But as I said, perhaps this is more philosophical than technical. Let me say friction for me is the umbrella thing, but I specify more in detail which type of friction. Is it abrasive friction? And I hope there are not tribological scientists now listening to me, because I'm saying very dangerous things perhaps. But there is abrasive friction, there is adhesive friction. So say friction is the umbrella. But I think if we want to control wear patterns on cutting edges, friction is too wide. We need to be more specified in what exactly leads to certain wear patterns. Time flies. I see there are more questions, and please put in your questions in the chat. Afterwards, I'll spend the needed time for trying to answer all the questions. But here I want to respect the time. I hope it was an interesting 45 minutes we spent together here. It's a very important subject, could be the most important one that's discussable, but it's for sure the most complex thing. Tool deterioration, tool wear, and how to manage it. And perhaps the most important question, but as I said, that is for the next time, that is, how long do I allow a tool to deteriorate? When do I decide, now I stop, now it's time to replace? Whatever type of wear you see on a cutting edge. That's the question about tool life. And that's the main subject for next time. And I would like to invite you for the next event, because only when you have both sides we can come to real conclusions. What is the deterioration? What type? How big? And what is the time? And if we combine the two, that's the moment we talk about controllable, productive, sustainable machining processes. Thank you very much. I hope it was an interesting session, and I'm looking forward to see you in the next session. And don't forget tomorrow the webinar on square shoulder machining, where one of the subjects is very specific, tool wear, but very specific then in square shoulder milling. Thank you very much.